Welcome to video 8.1 in our first Principles of Astrophotography series. In this video we discuss diffraction, a fundamental property of the wave nature of light that causes it to bend around obstacles.
Because of diffraction, pinpoint stars in the field of view don't yield pinpoint star images on the sensor, even under perfect conditions.
Instead, pinpoint stars produce target-shaped patterns on the sensor, called Airy patterns, with larger telescope apertures yielding smaller patterns.
Yeah. If you're an outdoorsman, you can print one of these off and stick it down the range. It'll work. This means that, because it's a target.
Yeah, I got that.
This means
I worked that much out, believe it or not, yeah.
Larger aperture telescopes can produce higher resolution images.
This video is based on section 8.1 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. All right, review. Image formation.
Yeah, so in a previous video, we talked about how images are formed. A point in the field of view gets mapped to a point in the image plane, and that each different point in the field of view gets mapped to a different point on the sensor, and that's how you get an image.
And in that video you said this is not true.
And I put a little proviso on there saying that this is a lie, and this is where we're going to correct the lie. So that's video 6.2, where we talked about that. Here's where the truth comes out. Diffraction means that light is going to bend around obstacles, and when light enters your telescope, it bends around this obstacle, and that disrupts the idea of a pinpoint mapping from one point to the other. So it's the bending of light around obstacles owing to its wave nature. So in this graphic, we have light, or any kind of a wave actually. The black lines, the vertical black lines corresponding to troughs in the wave, and the white lines corresponding to peaks in the wave. And so the distance between these two black lines would be the wavelength. Okay? So then it hits this obstacle like you would see in, and you can look up videos on YouTube that show you what happens when waves come into an inlet and then they diffract in this interesting way. But what you can see is that the nice regular pattern of waves before it hits the inlet gets disrupted into this diffraction pattern. And you get places where there's where the waves line up, and you get more motion of the waves, and that's called constructive interference. And places where the peak of one wave corresponds with the trough of the other, and that kind of levels out the wave and makes it less strong there.
Principle 108, Airy pattern. Diffraction converts stars in the field of view into Airy patterns on the sensor.
So this is what we talked about in the intro, where you take a pinpoint star in the field of view, it produces this target-shaped Airy pattern.
We're looking for a bullseye here, though, not a target shape.
That's right. Well, here's your bullseye right here, and that's called the diffraction. Well, it's called the Airy disk. Sorry. But you can also see, and I think you'll be able to see in the video, that there are diffraction rings. Outside that Airy disk. So here in this diagram, white means bright light, and dark means no light. So if you plot this, so what I'm going to do next, this angle theta is the angle on the sky, And next I'm going to show you what this looks like in 3D. This is again the angle on the sky. You get really bright here, bright in the center. And that's where the pinpoint, where the image pinpoint, that's where the pinpoint would have been, is where that bright spot is on the sensor. But then you see these diffraction rings.
That's a cool graphic.
It's really pretty. You can begin to see a small ring right around here. Then I want to show this to you one more way. And then we'll let you read this principle. So this is again, the angle theta. Theta equals 0 coincides with the center of the star's Airy pattern on the sensor.
Mm-hmm.
And that's where the brightness or the intensity, and that's what this I stands for, is intensity. And it's a function of the angle on the sky. So the intensity starts big, goes to 0. And where it goes to 0 is called the disk radius. Maybe I'll just go ahead and cover this one if that's all right. Yeah. So theta naught is where the intensity goes to 0. That's where that black ring was here. So here's theta naught. That's where the black ring is, and then there's a just outside the Airy disk and just before the first ring. Here, this is where theta 0 is, right there where it reaches a minimum. This one, the reason I'm spending so much time on this one is that it's the origin of what's the very famous Rayleigh criterion or Rayleigh limit, which you'll find quoted on every telescope when you look at telescope advertisements. So there's a couple more ways you can measure the width of the Airy profile. One is the full width at half max. That's this quantity right here. So if you look at trace A, which is for a bright star, you say, okay, its maximum is 1. Half its maximum is going to be 0.5. That's what we mean by the half max part. This capital theta I is the full width at that half max. So at that position here, it's the distance between those 2 points. Distance between where the profile intersects these green vertical dotted lines. And so that's called the full width at half max. There's another diameter called the half flux diameter, which, as you can see, where the full width at half max is 1.029, about 1.03. The half flux diameter is 1.07, so they're only like 4% different from each other. And if we were to plot it, it would just be right bumped up against here. So this full width at half max is very close to the half flux diameter, theta f. So these are all measured in radians, all three of these formulas, and they're all independent of star brightness. In other words, if you've got 3 stars, a bright one, A, a medium one, B, and a dimmer one, C, you can see that star B, at half its maximum, it still has the same full width. So star B reaches its maximum of 0.5. Half of that maximum is 0.25, right? But you notice that that half maximum is the same as it was for star A. Same thing with star C. At half maximum, it still has the same width. You might be asking, well, why are you worried about this? Because it's crucial in understanding star sizes. Several videos from now, we'll talk about the implications of that for star sizes. But all of these do depend on something. And lambda here is the wavelength of light. So, what does that say about the full width at half maximum as a function of wavelength for red light versus blue light? Well, red light has a higher, larger, longer wavelength
yeah.
than blue light. So that says that this full width at half max is going to be bigger for pure red light coming through than it is for blue light coming through. So one embarrassing thing about that is that when you're imaging the Airy disks, so if you have a star that has both red light and blue light, which all stars do, the red Airy disk is going to be bigger than the blue Airy disk.
Right.
It's just life.
Because it's the larger wavelength.
Yeah. Okay, and then D here is the telescope aperture. It's the diameter of the main lens or mirror in the telescope. So what does this formula say about the size of the Airy profile as a function of the size of your telescope? And the answer is, the bigger your telescope, the bigger the aperture will be, and the smaller the full width at half max will be, which says that the stars are going to, as you get a telescope that get 1,000 meters on the side, then you're going to get more pinpoint stars. Bigger the telescope, better the resolution. Thanks for watching.
And we'll see you next time.